This is problem 79 solved by Rich Raffin and Phil Savage. Consider a thin, i.e. it has essentially no thickness in the Z3 direction, circular membrane of radius r initially lying in the Z1, Z2 plane as shown in the sketch. Under pressure, the membrane deforms into a bubble according to the following deformation map. In this deformation map, beta is a constant, as well as big R is a constant, which represents the radius of the circle. Little r is defined as a vector in the radial direction, as can be seen here. The problem first asks to find the deformation gradient. The definition of a deformation gradient can be seen here. We then apply this to the map that was seen in the problem statement, and we get an answer, a matrix that looks like this. We then substitute in r, the vector r, for simplicity, and the matrix then looks like this. The next portion of the problem asks to find the radial stretch. When we look at the vector in the radius direction, the length of that vector is equal to z1 squared plus z2 squared, square root of that. And that is equal to r. If we apply that to a unit vector at n, it is equal to z1 times e1 plus z2 times e2 over r. We will now look to solve for lambda n, the stretch in the radial direction, which is equal to the length of the vector fn. F operating on n is then equal to z1 over r, e1, z2 over r, e2, minus beta pi 2r sine of pi r over 2r in the e3 direction. Lambda n is then the magnitude of this vector, which can be seen here. Simply taking the square root of the sum of all the squares in that vector, of the components of that vector. Lambda n is then equal to the square root of 1 plus beta squared pi squared over 4r squared times sine squared of pi r over 2r.
The next part of the problem asks us to compute the stretch and the direction that is in the initial plane of the membrane but is orthogonal to r. In other words, tangent to a circle centered at the origin. So to start off with, we define an arbitrary vector v with components v1, v2, v3, and then we operate f on v, and we get this vector v1, v2, and then this term. In order for v to be orthogonal to n, which we define as a unit vector in the radial direction, the dot product of these two vectors has to equal 0. And the dot product these two vectors would be z1 over r v1 plus z2 over r v2 equals 0. So if we go back to the result of f operating on v, we have this term in the E3 direction. That term is the dot product of v and n, so that term has to equal 0. And then we come down to here, and using the definition of the dot product, we find that negative z1 over r v1 has to equal z2 over r v2. So then we say, if we set v1 equal to negative z2 over r, then v2 has to equal z1 over r. And we can see, plugging in, that we get z1, z2 over r on both sides. Therefore, v, our vector v, is orthogonal to the vector n. So the final f operating on v is negative z2 over r, z1 over r, 0. And the stretch in the v direction is, as before, the square root of the squares of the components of the FV vector. And the final answer, when you substitute 1 in for z2 squared plus z1 squared over r squared, you get 1 as your stretch. To illustrate what the vector v looks like, we have our vector r, which has a z1 component and a z2 component. The orthogonal vector, which we call v, has a negative z2 component in the e1 direction and a positive z1 component, or excuse me, a negative z2 component in the e1 direction and a positive z2 component in the e2 direction. Next, the book asks if these two directions are principal directions, meaning unit vectors v and n. So in order to make this problem a little simpler, we're going to define the constant a equal to b pi over 2r sine of pi r over 2r. By doing this, we can simplify the gradient map into this matrix, and then we took the transpose of that same matrix in terms of A. Then we found C, which is F transpose F, and we got this result for C. Now, we remember that our vectors for n and v are z1 over r, z2 over r, 0, and v negative z1, or excuse me, negative z2 over r, z1 over r, 0. So C operating on n gives us this vector, and if you'll notice, we have a z1 squared term here, a z2 squared term here, and they're both over r squared. If we pull those values out and set them in terms of a squared, they equal 1. So we end up with z1r times 1 over a squared and z2r times 1 over a squared. So we can pull that 1 plus a squared out, and we get 1 plus a squared, which is just an eigenvalue, times our vector n. So since C operating on n is equal to n times an eigenvalue, then n is in the principal direction. We do a similar thing for V, we have C operating on V, and we come out with the vector V on the other end. So we have an eigenvalue of 1, and as with N, since C operating on V is equal to an eigenvalue times V, V is in a principal direction as well.
Problem statement then asks for the deformed length in the radial direction. So this refers back to our stretch in the radial direction, lambda n, which is equal to the square root of 1 plus beta squared pi squared over 4r squared times the square of the sine of pi r over 2r. The deformed length can be defined as the integral from 0 to r in the radial direction, so that's from the center of the circle out to the edge of the circle, 0 to r, of this stretch integrated in the radial direction. This is because the stretch changes over the radius of the circle. It is not constant, so therefore it must be integrated. This integral then looks like this, where we have the deformed length is equal to the integral from 0 to r of the stretch that we just explained, dr. Finally, the problem statement asks for the slope of the membrane at the edge after deformation. This is a picture from the side of the deformed shape of the bubble with the Z3 direction pointing upwards. You can see that the unit vector in the radial direction n is pointing off to the right, and Fn is pointing as a tangent to the slope at the edge of the circle of this deformed shape. The angle between those two vectors is the slope that we are looking for. To find the angle, we simply perform a dot product of n dot Fn, which can be seen here. When we solve for the cosine of the angle, we then get the dot product of n dot Fn over the magnitudes of n times the magnitude of Fn. When we substitute in 1 for the magnitude of n because it's a unit vector, and the stretch of n for Fn, for the magnitude of Fn, we then have n dot Fn over 1 divided by the stretch of n. We then solve for the dot product of n dot Fn, which is z1 over r, z2 over r, 0, dot product z1 over r, z2 over r, minus beta pi over 2r, sine of pi r over 2r. This is equal to zeta 1 squared over r squared plus zeta 2 squared over r squared, which can be simplified to 1. Substituting this back into our equation, we have theta is equal to cosine, the inverse cosine of 1 over the stretch in the radial direction. This is then equal to the slope that can be seen here.